Hi guys, and welcome to today's video. Today we're going to take a break, kind of, from equations and talk about relations and functions. So we're actually going to go through two sections today, 1.6 and 1.7. Let's get started. So first up, some vocabulary words. A relation can be represented by a set of ordered pairs. Oops, right. Okay, thank you. All right, ordered pairs. Now, an ordered pair is two numbers in a parentheses. So you have like 2, comma, -5. All right, and this first one is the x, second one is the y. So x, comma, y, like that. Now, the domain is a set of all the x values. All right, and the range is the set of all the y values. Right? So whenever we're talking about domain and range, what we're asking is what are all the values that x can be? Or what are all the values that y can be? Okay, so keep that in your brain. Domain is all possible x values. The range is all possible y values. Now the independent variable is the same thing as the x values and the domain. And if you hear about an independent value, you're talking about the x values. The dependent variable is the y values, or the range. All right. Now, what exactly is a relation? Well, a relation is a function if for every x value, there's exactly one y value. All right, so anytime you can put an x in and get a y out, you have a function. You have a relation. Each value in the domain of the function is called the input, and each value that comes out is called the output. Okay, so you can almost think about it as the function or the relation as like a machine or one of those factory lines. X goes in and then y comes out. And that's going to be the relation for all the functions that we're talking about, which is why it's called a relation. This is the relationship between x and y and how they work together. Now, let's talk domain and range. Again, the domain is all possible x values. The range is all possible y values. So now we're going to list this in set notation. So we'll do the domain. And now, when you're doing this, you don't have to put them in any particular order. So I'm just going across like this. But you see how over here we have another -2. Okay, well, I already have -2. Set notation is a list of all possible answers. I already have -2 in my list. So I'm not going to do repeats. You don't need to repeat elements in set notation. All right, let's go to the range. So I have 0, 3, -7, and 1. No repeats there, so we're just going to plug them all in. And there you have it, domain and range. You do the next one. And there you go. Sweet and simple. All you have to remember is that while they can be in any order, set notation does not do repeats. Now, when we are reading about graphs, this part is not on the guided notes. Now, if you're following along in the guided notes, this little bit is not on there. So in a margin, on a separate sheet of paper, you can take notes on this slide, and then we'll go back to the guided notes. In general, when you are reading graphs, the graph is literally a picture of what's happening. So you can think very, very logically about what a situation would look like, and that's your graph. So the first one, the graph represents the distance Francesca has ridden on her bike. Describe what's happening. Well, if we look at this, our independent value is time. Time is almost always going to be our independent value, and y is going to be our distance. So when she's riding this bike, we have a very steep incline, which probably means she took off and she was moving. All right, she got a lot of ground in a very little time, and then she kind of just stalled out, going at the exact, she stopped maybe. She didn't go very far. She didn't go anywhere. And then she's moving again. She went straight up. So maybe she was riding her bike and stopped at a light and then started going again. These are all different stories that we could create about these graphs. And this helps us to kind of figure out what they're describing. And when we do put numbers on the graph, it helps us understand what they're trying to get across. Now look at these two bottom ones. You don't have to do both, but I do want you to pick one and sketch it in your notes and write a brief blurb about what it could mean and just small little story to it. Okay? You are trying to understand what the graph means. So that was all of 1.6, relations, understanding, domain, range, independent, dependent value, and being able to look at graphs and understand what they're trying to convey. Now we're going to get a little further into math speak and talk about functions. We're now in section 1.7. Just going lightning quick. All right, so when you're given a graph or picture relation, you're asked if it's a function. The easiest, most direct way to do is just to look at it and see if it passes the vertical line test. Now this is when you move your pencil or a ruler or a straight vertical line across a graph. And you are looking to see if the line has to be vertical, if it intersects at more than one point. So you want to know if each x value is paired with only one y value. So if I were to draw a graph up here in the margin, and I had this graph right here, and I were to take my pencil and I were to move it from left to right, because we do math the same way we read, from left to right. Everywhere my pencil touches this graph, this line, it's only going to have one x and one y, even when it looks like this. Okay, let's do a curve. All right, one x to one y. Now let's erase one of these, and I'll show you a failed test. Okay, a sideways curve. If I were to draw a vertical line, notice how it connects in two spots. There are two x's, or there are two y's for this one x value. And that's what makes it not a function. In a function, you have to have one x go to one y. Okay? That's the vertical line test. Now, there are different kinds of functions. You have discrete versus continuous. Discrete is when you have dots, like 6 and 7 here. These are examples of discrete, so there is no line. No line that connects the dots. Whereas the continuous graph, the continuous function, does have a line. The points are connected. Okay? Now it doesn't matter which one you use, discrete or continuous, they will all pass the vertical line test. Now, another way to represent functions other than graphs is mappings or tables. Mappings are they're very, very similar to each other, they just look different. Okay, so when you're mapping something, all right, it is where you have a diagram or table where each x value is paired with only one y value. So if you look down here, you see the two circles. This is actually an example of mapping. And the way you would read this is each arrow in the input, or each number in the input is an x. So this x goes to this y. So if I were to do it as a point, come over here off to the side, I could write this as 1, 0. And that's one ordered pair. And then I would go to 3 and 6. That's another one. And I could go to -2 and 3. And then I have 5 and -4. And so you can look and follow the arrows and create a list of ordered pairs based off of the elements. Now this one happens to be a function because each x value goes to only one y value. There are no repeat x values. And what a repeat x value would be is something like this, where I would draw another arrow from the 1, say like the 3. Okay? Because the one singular x is going to two different y's, now it's no longer a function. All right? One more example. What happens if the y's repeat? Okay, good question. Let's say I have this 3, and instead of going to the 6, I'm going to draw the line to the 0. Okay? So the 3 is not going to the 6, it's going to the 0. This is fine. Okay? I can have 1, 0 and 3, 0, and it would still be a function. It doesn't matter if the y's repeat. That's fine. It's only the x values that can't repeat. Now before we made our edits, the mapping of the last function was actually a one-to-one mapping, okay, or a one-to-one function. This is when every element of the range corresponds to exactly one singular element in the domain. Okay, so before we did our edits in the red, it was a one-to-one function. After the edits, it was no longer a one-to-one function. So in order to be a function, it has to pass the vertical line test. But in order to be a one-to-one function, it has to pass both the vertical line test, I'm going to abbreviate here, all right, and the one-to-one function. Okay, so 1x goes to 1y. So as I look down at number 18, is it one-to-one? Well, yes, it is. You look at your x's, none of the x's repeat. You look at your y's, none of the y's repeat. So yes, it is a function, and more specifically, a one-to-one function. On number 21, when I look at this, I look at my domain, none of the x values repeat, but on my range, I have a y value that repeats. So while this is a function, it is not a one-to-one function. So the answer here is no. Now once we've talked about functions, and once we know it is a function, now we need to talk about function notation. This is just a different way of writing the equation. Okay, so we've talked about how a relation is the x goes in to the function and the y comes out. But in algebra, there's a lot of different types of functions, and I'm already getting tired of saying that word in this one singular video. Function notation is a way to name the different relations, the different functions. That way, instead of saying the word over and over again, you can just see the symbol. The main symbol is f of x. F of x is the name of most functions. Other common names are g of x, h of x, and you can really use the whole alphabet, except for x and y. Now, function notation, the way this works is that anything in the parentheses, anything at all, okay, that's what goes into the equation. Because remember, x is your input. That's what you're putting into the equation. This right here is where the input lives. So anything they put in there, they want you to put in the equation itself. So let's do a few examples. Over here at 4a, we have f of x is equal to 2x minus 3. This first one tells us f of 1. So what we're going to do is we're going to take f of 1, and I'm going to plug it in to the x coordinate, or the x spot. And now you solve. 2 minus 3, f of 1 is equal to negative 1. What this means is that if we were to have this graph drawn out on a coordinate plane, you would find a point at 1 comma negative 1. That'd be where your point is. And then we can do the other one. We can plug this in. So now I have f of negative 2 is equal to 2 times negative 2 minus 3. This would be negative 4 minus 3, which means f of negative 2 is equal to a negative 7. So on this same graph, you would have a point that is negative 2, negative 7. All right, your turn. Do number 5a and 5c. And there are your answers. On this graph, where x is 4, y is 128, and where x is negative 5, y is negative 250. And this is how you would read that. The x is truly your x value. Your answer is your y value. So if you can think about it in relation to a graph, it makes a little bit more sense. Now, whenever you're asked to fill in the table, then sketch a graph, literally what they want you to do is take the x coordinates that they give you in the domain and plug them into the function and see what you get. So what you're going to do is you're going to take f of negative 6, this first value, equals 3 minus 4 times negative 6, and you're just going to plug it straight on in. So 3 plus 24, and f of negative 6 is going to be 27. And you can fill in the rest of the table like that. Now when we get down here to the bottom, we're given negative 5. okay? Remember, this is the y value, which means you can rewrite, I'm going to do it over here, f of x is equal to 3 minus 4x. You can rewrite this whole equation as y is equal to 3 minus 4x. And since negative 5 is y, I can plug it into this value right here. Now I'm going to change colors. So what you have is you have negative 5 is equal to 3 minus 4x. And now you have an equation where you can solve for x. So subtract 3 from both sides. And that's going to give us a negative 8 is equal to negative 4x, which means we have 2 is equal to x. And that's your leftover x value. These are your ordered pairs. These are your coordinate points. You would now take these coordinate points and put them on the graph. So I only did the bottom 3 because those are the only ones that would fit on this graph, but you could also plot the other ones at negative 315 and at negative 627. Now in this one, instead of being given an equation, we're given the actual picture graph itself. We're still given our x values. Now we have to find the y values. So what we're going to do is we're going to look. These are our x values. So when x is negative 2, what's happening? So I'm going to go to my graph, and negative 1, negative 2, my y value is right here at 1, 2, 3, 4, positive 4. And the next one, where f is 1, or x is 1, I'm going to go over. Here's where x is 1, and then I go down, and you kind of got, what is that, 1.75-ish, negative? Okay, so the downside of having picture graphs like this, where you can actually look at it, is that the graphs aren't exactly accurate. If you had an equation, you could at least end up with a fraction. Here, you're just going for your best guess. Now the next two tell you what the y value is. Look on the graph and see if you can find what the x values are. All right, so the first one's kind of hard to tell, but you go to where y is equal to 1/2, which I picked as right about there. Then you go over to the graph, and then you go straight up to see what x coordinate you're on. Again, it's hard to tell, so I ballparked it at 1/4. The next one's easier, negative 2. So you go down to negative 2. You go over to where it is on the graph, which is right here, and then go straight up. This one's a nice, neat point, and you can easily see that x is on 2. And that's all there is to it. You look at the x or look at the y and see where it matches up on the graph. All right, and this is the end of today's lesson. Have a good one, guys. If you have any questions, please let me know. Otherwise, I'll see you next time.